All right, so welcome everybody. I'm really glad you made it to my slot. I know after lunch is a tough time, and especially with so many other great talks going on, I feel really honored that you're here. So thanks. So first question: can you raise your hand if you recognize the movie where these artifacts come from? Yes. Wow, I have a crowd full of Indiana Jones lovers. Well done. Yeah, so that's where we start. A couple of notes to introduce this talk. First one, my co-speaker is on holiday. At the moment, he's on Bali, I think, and he's a great guy, so I thought it's right to pay him credit. Of the two, he was the Kubernetes magician, so I'll do my best to cover his part, but don't throw too much rotten vegetables at the end if I don't know some answers to some questions. Actually, the crowd maybe will help. Then, I'm going to touch a lot of different concepts, but I will only mention the most important core ideas about those concepts. So, let's say I'll talk about Akka actors. I will only mention the features of actors that are relevant for this talk. Same for Kubernetes and any other thing I will mention. And also, slides use pseudocode. So, and this is because I don't like, code walls in presentations. So it's a pseudocode. So those who know what's missing will know, and those who don't will get only the basic concept and not confused by the rest. Right, so we can start. My name is Fabio Tiriticco, and I'm a software developer. Worked as a tech lead lately. My handle is TicoFab, pretty much everywhere on the internet, Twitter, LinkedIn, GitHub, all of that. And as mentioned by Arno, I come from Italy, but I've been living in the Netherlands for a long time. And a few fun facts about me. I love cycling and touring on my bicycle. That's a couple of years back. I cycled all the way from Amsterdam to Rome, which is my hometown. In Amsterdam, I also had a business of selling Italian snacks on the street. That is Kingsdag. It's the day of the king in the Netherlands, and it's a big party where everybody sells whatever on the street. And I was selling arrosticini. If someone from Italy knows them, that's it. And when I was quite young, I used to play the bass guitar in a Pixies cover band. But fortunately for me, my biggest passion is also what I do for a profession. And that's why I created and I run a meetup in Amsterdam called Reactive Amsterdam. Well, we talk about everything reactive. And it's been going on for a few years now, and we've had big sponsors, and I'm really happy with the community there. Now, every talk about reactive has to start by mentioning the Reactive Manifesto. Written in 2013, the first version by Jonas Bonner and those other guys, which luckily for us, they're here. I think 75% of those guys are here at the conference. So yeah, we can go talk to them. It's quite nice. But the best wording to describe the Reactive Manifesto, I've actually heard it from Jamie Allen in one of his latest keynotes. That is, we like to build elastic and resilient systems via message-driven architectures in order to deliver responsive experience to our users. And today, as introduced, we're going to focus on one trait of that, which is elasticity. So elasticity, in few words, is the ability to react to the varying load that hits your services. Because actually, if you think about it, all services have some sort of seasonality or variations in traffic. You can think, I don't know, Amazon probably has, during Black Friday, maybe a higher peak of traffic. Spike. Maybe a local newspaper will have most of its traffic during daytime and not during nighttime. Maybe a bank has a lot of traffic at the end of the month when it's payday and things like that. So almost every service you can think of has varying traffic. And the capacity of being elastic is exactly that, being able to respond accordingly to these variations. Especially nowadays that we run things in the cloud, and of course we pay for what we use. So the idea is that we should be able to scale up or scale out, but also scale down when resources are not needed anymore. And yeah, in one sentence, elasticity is used just the right amount. Now, Akka is a toolkit that helps you achieve these reactive traits, and Akka's building blocks are actors. Actors, you can think about it as, the way I see it is, they're isolated islands of computation. So each actor can have state and behavior logic. So for instance, maybe every actor has a name. We have Bob, Tim, and Joe. But what's interesting about them is that in the usual average object-oriented language, you would check the name of an actor by doing something like this. My actor3, your instance.getName or something. Here, you can't do that. It's forbidden. The only way you can deal with them is through messaging. So each actor has an addressable mailbox to receive and send messages, and that's the only way you can interact with it. So, for instance, if actor 1, Bobs, wants to know the name of actor 3, he'll send a message saying, "What's your name?" And Joe will respond with a message, "My name is Joe." So this has many, many benefits. Isolation, these messages are asynchronous. But to me, the coolest one is that this really lets you model the world in a much closer way. Because if you think about it, this kind of asynchronous messaging is how the world works. If you want to know my name, you're not going to read some variable in my brain and you're going to ask me what's your name, and I'll tell you my name is Fabio. And so when you model things like that, everything all of a sudden goes a lot closer to reality, which makes it easier to reason about. Well, soon enough you will be able to read my brain, but we're not there yet, I think. I would like to show you an example of this modeling by talking to you very briefly about my first journey in the reactive world. Back in maybe 2013 or 14, a few years ago, I had this idea where I wanted to create an engine that lets devices, like smartphones, so enable basically cross-device communication via gestures. So you could pinch across the screen, across 2 screens, or maybe swipe across screens. And I built that. I sort of tried to bootstrap it as a viable thing. And so here's a small video that shows a couple of use cases. The first one was in education. So imagine a school where 2 students have this chemical app. And so if they have 2 hydrogen molecules, they can pinch and could create more molecules. Then maybe another student comes around and he has oxygen. And then you can pinch and you can create water and things like that. Another use case that I built was transferring pictures. Just select picture on your phone and then, let's see, swipe it, and boom. So, it was very naive, and we didn't really manage to pull it off, but it was fun to work on. Obviously, it's a lot easier to do this with WhatsApp. So, I think that's why it didn't really go very far, this idea. But it worked. Actually, if I look at the code that I wrote 4 years ago, I feel deeply ashamed of what I wrote. But I think that's kind of normal when you learn new things and improve yourself. I think it's a good sign. But anyway, about the modeling. So look at it like this. If you have all these phones that connect to your service, to your central API or server or whatever, you have all these phones, and then you can map each phone to one actor. And then each actor will have the location of this phone, all the information about it. And then you have maybe another matcher actor that checks if 2 phones are matching. And then if it detects that 2 phones are matching, let's say phone 1 and phone 4, then it will send a message to the first phone saying, "You matched with phone 4, and this is his address." Another message will fly over to phone 4 saying, "You matched with phone 1, and this is his address." And at that point, the 2 phones will exchange messages between them. So isn't it kind of close to reality? Here, in this actor programming approach, you don't really reason about interfaces between objects, but more about the protocol of their communication, how they enable behaviors by talking to each other. And now, I'm sure you see where I'm going. Imagine that my startup was hugely successful, and I had millions of users. I wish. But imagine that. I would have needed to scale out. Would it have been difficult to scale out? To answer that question, we need to look at a concept called location transparency. So imagine that's me in Australia, and that's my co-speaker in New York. If he wants to send me an email, he doesn't need to know whether I'm in Australia or in Siberia, because all he needs to have is my email address. And the very same thing happens between actors. So once you have programmed your code and behaviors around addresses, it will work seamlessly, both locally and remotely. So all you have to do is take one of the actors and move it to another node. And the code you've written will work exactly the same. In Scala, it works. The syntax is like this. So if Bob wants to send a message to Tim, then you need to have the address of Tim, and then exclamation mark means send the message to, and then ask what is your name. Now, given this, this addressability helps you scale up or down stuff that you have already written, and so that's really cool for me. So let's look at the little elasticity test system that I built for this demo. Of all the reactive principles, elasticity was the one that always scared me the most, because I'm not a DevOps guy, or I know very little about it, and to achieve this elasticity, you need an infrastructure that supports your app, scaling up or down. So I really wanted to make this work, and I built this system where you have very simple, four or five actors. You have a job source. It's a guy that emits continuously job to be done. These are just examples, but it could be, I don't know, users to serve or something like that. This job source embeds a little HTTP server so that I'm able to adjust the rate of the jobs that are sent out. Now, these jobs are then picked up. Oops, sorry. Man, this. Yes, these jobs are picked up by a master actor, which will then distribute them to a set of workers. And of course, the more workers you have, the more jobs you can consume. Let's look very briefly at the worker. This is essentially it. You have a worker that extends actor object, and then at some point within the code, you will have a case job. That means that it received a job, and then we'll just simulate some CPU-intensive workload, and when we're done, we will send a message to the master saying we completed our job. What's really important about what I just said is that there is a feedback here. And so if all the workers send a message back to the master, then the master can put in place some logic to see, oh, wait a minute, I am consuming way less jobs or way more jobs, way less jobs than necessary. And so the master has the power to decide when it's time to scale up or down, which is why we introduce a scaling controller there. If the master detects a situation where there's too little power, it can just send a message to the scaling controller saying, please add a node. Magically, we'll see how it works. A new worker will appear, and the master will be able to send works to that guy as well. Similar thing. If there is too much power, we will just send a remove node message to the scaling controller, which will end up in one of the worker disappearing. So this is quite elastic. The more jobs we have, the more worker we'll have, and vice versa. Now, issue number one, how to distribute this. Akka helps you with this as well. There's a module called Akka Cluster. Akka Cluster, very, very simply, works like this. You need to specify a couple of nodes that will be the seed nodes. And with node, I don't mean actors. These are not actors. These are, think about it for simplicity, just each node is a JVM. So nodes will be the guys that everybody needs to register to. So when there's more JVMs coming, they will need to talk to the seed nodes, say, hey, I'm here. And once that is done, they will create a cluster where they can all share information and communicate with each other. Akka Cluster offers a simple membership service where each node has a state assigned, so a node can be joining, can be up, can be leaving, unreachable, and so on. And so the only important thing here is that nodes need to know where the seed is. So the seed need to be reachable. So you need to know its IP address or DNS or something, but be able to reach it. But given that, everything you've already created can be just clusterized with almost zero effort, just some plumbing. So in our case, what we will do is we start from a local single JVM and things will just work. But then we can make one JVM will be the seed and it will contain maybe those 3 actors, job source, master, and scaling controller. And then each worker will be assigned to its own JVM. So pretty nice. But then at this point, how do we spin up and shut down nodes? And that's where Docker and Kubernetes come in. I'm going to skip the Docker part, but just a couple of words why we chose Kubernetes for this experiment. Well, because it's able to spin up and down nodes, so answering our question right away, but also it has features like resilience, so if a node goes down, it will detect it and restart it. Kubernetes is seeing huge mainstream adoption. It's kind of hyped, but everybody's on it, which is why cloud providers like Google or Amazon and Azure, they're all offering Kubernetes services, and most importantly, there's APIs. So you already see where I'm going. The scaling controller is becoming now a Kubernetes controller. And I was kind of happy about that cheesy animation you just saw. If we look inside the Kubernetes controller, it's really as simple as it gets. Stripped down to the bone, it's an actor that will receive 2 kinds of messages, add node and remove node. That's it. And what follows next is Kubernetes specific API. We can give a look later, but actor-wise, that's all it does. As simple as that. How do we use it? Well, just as simple. The master will do its own logic to see whether we have enough or less resources, and send a message to the Kubernetes controller, please add a node or remove it. Before, I have a small demo, but before the last few things, I just want to show the architecture a little bit. This is what we have already seen, all the actors on different JVMs, workers and master and all that. But then on the Kubernetes layer, we need to introduce a couple of concepts. So pods. Pods are the basic computation unit in Kubernetes. Each pod basically will contain one or more containers and actually run your services. In this example, each pod will contain 1 container. So it's either a master or a worker. Below the pods, we have these controllers. We have this controllers layer. Basically, a controller in Kubernetes, it's called deployment in our case. It's like a waiter at a bar. You basically ask the controller, what do you want? So you might ask this controller, I want 7 workers, and it will make it happen. It's just like a menu thing that you choose and order. And then below them, we have services. Services are logical entities that work with single pods or more pods. Easier to explain what they do. We'll have 2 services here. A DNS one, because remember that the master needs to be addressable, the seed node. And then we'll have a little HTTP service that is for the job source. Remember, I need to be able to change the rate of the job emission. So this is more or less our architecture. We're going to give a glance at the code and then see a little demo that I recorded. So let me switch to that. Okay, you can probably read it. Oh, better. You can maybe still read it. Can you? Well, so this is our configuration file. The only thing I want you to look at is there's a little cluster configuration here, out of which the only important thing you need to know is this line. remember I told you that the nodes, the seed nodes need to be acknowledgeable. And so this is the only one thing that you need to specify. They need to have a fixed reachable address. This is, well, technicalities, but this is the port, you know, and this is how you reach it. And this needs to be known to every node that wants to join. And then I want to show you maybe briefly the master. Actually, let's do first the Kubernetes controller somewhere. There it is. Kubernetes controller. There you go. Just focus on two things. Add node, and then this is some Kubernetes API logic. And this other message, remove node. That's it. And then this is all, again, logic in Kubernetes API. It's the Java API, so you have all these horrible builders and stuff. Sorry, didn't mean to offend anybody. But yeah, and then we go check the master. And so the master is a little more interesting. Can receive a job to execute from the input source and do stuff. Can receive a job completed messages if a job has been completed. And then every so often, it will evaluate the rate. And so this is just logic that I have written to understand when we have more power or less power than we need. Nothing really fancy, actually. Well, if you want, it's on GitHub, and if you want to improve it, please send me a PR. Yeah, so this is in code the concepts that I've shown you earlier. And then, so let's get to the meat, or fish, because Malaga is big about fish. There's a GUI, user interfaces for Kubernetes, but we went really bare bone, and so you're going to look at the terminal for a little bit. So what I'm doing here, this bottom, yeah, maybe not. It's a little small. Maybe with the lights off. Better, nice. Sorry that it's a bit small, but it's. So here, this command is going to watch the status of my Kubernetes cluster. So at the moment, there's the HTTP and the Akka master DNS, so that it has a fixed reachable IP, and the HTTP server that I can just use to increase or decrease the rate. And then up here, I'm going to actually start the whole computation. So by starting this file that describes the Kubernetes cluster, you see that down here, pods are being created, and this is a deployment that's being created, if you remember the architecture earlier on. And now, I am going to use that IP address to check if it's alive, and also to set the rate to 3 jobs per second. And the very friendly message is in nanoseconds. But there's 3 jobs per second. What happens here is that you see that the master is already starting to forward work to the workers. And so if we look at the logs, what's going on the master, yeah, these 3 lines are the moments when we evaluate the rate. So we see the queue size, how many workers we have, and the burn down rate. Burn down as in the difference between jobs that arrive and jobs that we consume. And so when we realize that we need more power, the master will ask the scaling controller to add another worker, and here now there's 3. And so we see that a member joined, and this is its address. And so if we wait another little bit, see these letters here, they're the name of the workers. So you see the C1, C3, because it's different workers. And then if we wait another little bit, yeah, here it is. Another worker is being created because we have 103 jobs in the queue, so we need to burn them down. And so it goes on and on like this. Just don't want to bore you too much, but if I skip very quickly to, so here, yeah, here we reach the point where, see, we have too much power now for what we need, because so it added a lot of workers until the whole queue waiting was burned, and now we have enough workers to burn all the jobs that come. And so if we burn down all these jobs that come, now you see that the burn down rate is negative. We are burning more jobs than they come. Then there you go, terminating, because the master realized that. And until it stabilizes, when the burn down rate is a little negative, not zero, you want to have a little more power just in case to react quickly, and then it will stabilize. Then in a little bit, I am going to, yeah, here, see, I am going to set to 1, the 1 job per second, so a lot less than what we have now. And the master will immediately realize and start killing workers. Yeah, see, terminating, and it will kill them all until I think there's, I wanted to say until there's 1 left, but really there's until there's 2 left. Yeah, so this is, to me, this, I mean, I was very excited when I saw this happening for the first time. It was really like, wow, this is elasticity at its prime, in a sense. And yeah, so I think there's nothing more to see. Yeah, so we reached the amount of 2 workers and we're stable. So if we go back to the talk. Yeah, so what I've seen is if you look at the burn down rate pattern, it's usually like this. So if it increases, then the burn down goes up, because remember, we're burning less jobs than we should, and then it burns a lot of them, but then eventually becomes negative, and then it will kill workers right here and stabilize. Obviously, this is the same if the job rate decreases. And this is an actual measurement that I did with real values. And indeed, so the blue one here is the jobs in the queue. So in the beginning, there's no workers, so jobs keep accumulating. And the yellow line is the amount of workers. So here we are adding more and more workers until there's so many at this point that the burn down rate is negative, because we're actually burning both new jobs and the jobs in the queue. Well, actually the ones in the queue first, but all in all, more than come, until the jobs queue decreases, and that's when we start killing workers. So here we kill a couple, and then it stabilizes. And then if here, again, is what we just saw. If here I lower the rate, then we'll also kill a couple more workers and stabilize again. So I'm almost done. For me, this was a lot of fun to do. But then I hear already some questions about saying, so if Kubernetes does all this for you, why wouldn't you use HTTP? Why would you use Akka Cluster and remote messaging? And well, something for sure is HTTP is ubiquitous. I hope I spelled it right. Everybody knows HTTP. It's used everywhere. There's libraries for every possible language. So that's an advantage, obviously, especially if you have legacy situations and maybe you have services already written and things like that. But Akka also has a few things. In particular, if you decide to build a system with Akka and actors, well, at that point, you have already built in elasticity and a way to communicate with each other. Asynchronous messaging gives you more control because it enables you well, to do a lot of things that we didn't discuss very much, but if you watched Roland Kuhn's talk just before lunch, he mentioned a lot of design patterns, and they are pretty much all enabled by asynchronous messaging between your components. I think it's less complexity. You know, for HTTP, you should import an HTTP library, a JSON parser, or things like that, define routes and REST and endpoints and all that. And plus, which I think is a big advantage, actors don't necessarily need a response. HTTP is a strictly request-response protocol, but actors, you could just tell something, just send a message out there. And so what you build, with this in mind, you don't necessarily need to wait for a response, which is also way more efficient. And actually, performance is another big factor. So if you're doing, you know, nothing extraordinary, then performance obviously is the last thing you should consider. But at a conference that was last week, or 2 weeks ago in Amsterdam, there was this guy, Johan Janssen, is another Dutch guy. He built an entire Lego entertainment park and put Raspberry Pis on all these components, and so they all move, and then they detect possible collisions, and they talk to each other. And each Raspberry Pi, like this one, they run a little JVM on it, and they communicate with each other using Akka Cluster. And then in his case, performance is really, really important, because a heavy thing like HTTP has a lot of overhead, consumes more power, it's slower. So he took some measurements. You can't read what's written there, but the green is HTTP, and the blue is the remote messaging. He had a few graphs, and this is the mean response time. And so when performance really matters, you want to stay away from HTTP, really. My personal advice is if you have actors and you don't have legacy services or something written in another language or Python, say for instance, if you don't have that but you only have actors, just try first with Akka Cluster and remote messaging, and then if you don't like it for some reason, then take the extra step of adding another HTTP library on top. Time to share with you my biggest learning of all this. Well, first, like on an emotional level, I was really happy again to see this elasticity really happening. But also my biggest learning is that reactive system design really is application design together with infrastructure. Build things with something in mind, how you're gonna run them. And I know you've heard this in 1,000 talks already, and you need to experiment yourself, but this was my personal biggest learning. It will force me to learn more DevOps stuff, which I'm not necessarily happy about, but this is my learning. I found, well, there's alternatives to Kubernetes, but I found Kubernetes to be easy to work with, simple, powerful. Oh yes, how about the Holy Grail? So, is that the right Holy Grail? Yes. Well, again, if you come here to this talk, you probably already know the answer, that there's no Holy Grail in software development. So maybe that Holy Grail was bad for this guy, but maybe it's right for you. Maybe you still want to try. I mean, I don't think so if you've seen the movie, but it could be the right one for you. That's all I had, so thanks, everybody. The code is there, if you want to look at it.
Okay, thanks. We can take